Okay, everybody, we're going to wrap this semester up with section 7.3. Let's jump right in. We're in this lesson. This one's sort of a it's going to be more of the chi-square testing, but it's comparable to in module 6, where we were looking at relationships between two variables. The difference is in module 6, the variables were both quantitative, and we're seeing if there's any way to determine a predictive relationship between them that we called correlation. In 7.3, we're going to look at two variables again, but here they're going to both be categorical variables, but we still want to see if there's a predictive relationship between them. Meaning, if you could tell me, the value of one outcome, or just, for a given individual, tell me how one variable comes out, what the outcome is for it, that I could have a better chance at predicting the outcome of the other variable, knowing the first. So that's the idea. When two variables have that sort of a relationship between them and they're categorical, we say that the variables are dependent. Okay, so here we go. Testing for independence with two-way tables. Introduction. In our previous lesson, we learned to use the chi-square distribution to conduct a goodness of fit test. This allowed us to compare theoretical expected frequencies from a null hypothesis to real observed frequencies observed in sample data. In this lesson, we'll continue with the chi-square tests in a special test for independence. Alright, so here's the context: marijuana and politics. The data used in this problem are based on an article, Attitudes About Marijuana and Political Views. From a random sample of 270 adults, the following frequencies regarding marijuana use were given. The two-way table below is missing several values. So you can see under political views we have 3 levels: liberal, conservative, or other. For pot smoking frequency, we have never, rarely, and frequently smoked marijuana, we didn't bother listing exactly what those mean, but they're well defined in the article. We'd like to investigate whether the variables political views and smoking frequency are independent of one another, or that there's a relationship or a no relationship between them. If they're independent, then there's no relationship. Alright, so the first question is, what's the explanatory variable in the experiment? There's not really a right answer to this. Maybe you think that people's political views are more likely to sort of be predictive of whether they smoke pot or not. But I'll go ahead and just go with that. There's not a right answer. You could say the pot smoking frequency just as easily, but here we'll say political views. Okay, and then the response variable is just the other variable, so here it would be pot smoking frequency. Okay, do I think they're related? That is to say, independent or dependent? Personally, again, this is just my opinion. I think that some political types are more likely to be smoking pot. So, but that's just my opinion. So I think they're dependent. And you can put whatever you want down here. There's not really a right answer. Okay, and to explain this, I would just say, I think that pot smoking frequency is higher among some groups, or political groups is what I really mean. I'm not going to expound on this, though. Okay, that's just what I think. Don't know if it's true or not. Okay, now, it says enter the missing values in the table above. Yes, so very conspicuously, there are values missing here. I'd like you to take a moment and just by subtracting, recognizing that, for instance, the first values in the first row have to add up to 155. That's enough to figure out what those values are. Go ahead and take a moment and just take 155 and subtract the other values in that row. Do the same thing with the other rows and columns. And why don't you go ahead and pause right now and fill that out. And I'll give you the answers in a sec. Okay, so what I got was 24, 3 by subtracting in the first two rows. And in the columns, 34, 9, and 17. And these add up exactly to the values that are the totals in the rows and columns. One thing to notice is that those values were not random that we entered, whereas the ones that are given in the table, these values, not the totals, but these 4 values that I've just circled, those could have been anything as long as they were less than the total. There was some randomness in those values, but once those 4 were known, the rest of them had no randomness at all. Okay, so we got this covered. It says compute the following conditional probabilities. Okay, the probability of being conservative given that we never smoke. Okay, so if it's given that that the person never smokes, we're picking one of these at random. We're only looking at these people. It is given that we're working with a never smoker. And the probability that that person is a conservative is 43 out of 173. So we can just divide that here. And if you compute that on your calculator, that comes out to about 0.249. Okay, the next one also has a given. It's the probability of being conservative with a different given. You're in the frequently smoke category. So when we look at the data table, it's different people now. Okay, we're looking at way down here with the frequently smokers. Now, the probability of being conservative is just 3 out of 44 based on this. 3 conservatives out of 44 altogether. So let's do that. Okay, and divide that on our calculators. So I get 0.068. Okay. So given your previous answer, and again, I'm saying that I think that your pot smoking frequently depends sort of on the group you're in. If you look at this, 24% among never smokers, 24.9% are conservatives. But among frequently smoking individuals, 6.8% are conservative. So it really does seem like the probability of being a conservative does depend on your pot smoking frequency. So I would say the variables seem dependent. I'm going to say evidently. This is not proof yet. The probability of being a conservative seems to depend on pot smoking frequency. And that's all it means to be dependent. Okay. Now in question 7, it says treat the row and column totals as constants and the observed frequencies as values that vary randomly from sample to sample. With the values originally given in the table, are the values you entered free random values, or are they dependent on the other values? I'm referring to these, the red values that were entered by us into the table here. Okay, those had to be what they were. There was no randomness. They have to add up to the totals. So those were not random values. I'm just going to say they were not random. And maybe they had to add up to the totals. I'll say the given totals. We had no choice in those values, so that's why they weren't random. Now it says if the degrees of freedom in the table are the observed frequencies, the degrees of freedom in the observed frequencies are the number of free independent observations, how many degrees of freedom are there among the observed frequencies in the table? Well, again, these values that we computed had to be what they were, but there was nobody telling us what these had to be. Those could be changed. It would affect the other values, but I'd say those 4 values are okay being random. So there's 4 degrees of freedom here. Okay. And now it's asking for a formula for the degrees of freedom. Let's read this real quick. It says, suppose a 2A table has R rows and C columns. Don't count the total row or the total column. Make a rule for degrees of freedom among the observed frequencies in the table. Express this rule as a formula for the degrees of freedom. Okay, so you can see it's a 3 by 3 table. All right, 3 rows. Okay, that's R equals 3. Okay, there are 3 columns. 1, 2, 3. So C equals 3. Okay. But when you look at the random values, it's not 3 times 3 equals 9 random values, because we've decided that, and I'm just going to cross out the values that aren't random here. So these values aren't random, and these values aren't random. Okay. The last column is not random. So you'd say if there are 3 columns, then there are 2 columns of random values. And if there are 3 rows, same thing. There's only 2 rows of random values. So you have to take the number of columns and subtract 1, and take the number of rows and subtract 1. So you end up with a 2 by 2 array of random values, and 2 times 2 is 4. That's the number of random values. You take the number of rows minus 1, take the number of columns minus 1, and multiply them. Okay, so here's the formula for the degrees of freedom. R is the number of rows. The last one doesn't count, because that has to be the row of values that make the totals. And then the number of columns minus 1, because the last column doesn't count. Okay, so that's the formula for the degrees of freedom on this test, and that's one of the major differences between this and the last test we did. It's just different degrees of freedom. Okay, next steps. Now that we understand the degrees of freedom in a 2A table, it's time to think about a hypothetical or a hypothesis test. This test is similar to the goodness of fit test already discussed, but the degrees of freedom are different as discussed, and the expected frequencies have a special formula. So we've got the degrees of freedom here. We've got to get the expected frequencies down. We are conducting a test for independence. Our political views independent of marijuana smoking frequency? To conduct a goodness of fit test, we construct expected frequencies based on the assumption that these variables are independent of one another, and that's going to be our null hypothesis. If A and B are independent, then this is a rule called the multiplication rule. We've talked about it a few times. The probability of A and B is equal to the probability of A times the probability of B. That will be true when the variables are independent. So suppose A is liberal and B is never smoke. Suppose we pick one of the sample individuals at random. Compute the following probability. So the probability of being a liberal and never smoking pot is the probability of being a liberal times the probability of never smoking pot if the two events are independent, which is what we're going to assume in our null hypothesis. So let's do the probability of being a liberal first. Going back to the table, probability of being a liberal is the total number of liberals, which is 155 out of the total group, 270. So it's 155 divided by 270. Okay, so that's the probability, again, of being a liberal. But we also want to multiply by the probability of being a never smoker. So back to the table. Altogether, the never smokers are 173 people. Never smoke pot altogether out of 270 people. So again, it's 173 divided by 270. Okay, now go ahead and pause while you do this computation, and then come back and I'll show you the answer. Okay, so I'm assuming you've done this, and the computation comes out to be 0.3678 if you keep 4 places after the decimal. Okay, about 36.78%. Okay, next we want to do the expected frequency. Now, just as a reminder, every chi-square test has a test statistic that looks like what? Let's find it real quick. So here's our chi-square test statistic. You have the observed frequencies here. You have the expected frequencies. And expected frequencies are always n times p. And what we just did was we computed a probability. So let's see if I can find that. Here's the p for our probability. Okay, and expected frequencies are n times p. So if you go back, you can remember that the n is 270. Okay, and then the p is 0.3678. Okay. So take a second and do that. Okay, so you should get approximately, I'm just going to round this to 99.3. This is the number of people that we expected would be in the liberal and never smoke category. Okay, that's called the expected frequency. But what was actually observed is 96. So let me show you that in the table. Okay, there were 96 people who considered themselves liberals and never smoked. So we just multiply the two probabilities. We expected 93.3, but we got 96. Okay, so that's pretty close. Sorry, it's 99.3, and we got 96. All right, so for this event, the null hypothesis of independence seems to lead to a reliable prediction of what actually occurred. We would have predicted 99.3, we got 96. That's pretty good. Okay, keep in mind this expected frequency is computed based on our null hypothesis that assumes our variables are independent. Look once more as we backtrack through the computation which we performed to compute the expected frequency. The expected frequency was n times p, which was the 270 times 0.368. Now, the 0.368 was another result of a computation, this one up here. So if you look, this computation is this computation down here, all being multiplied by 270. And again, if you look, the 270 appears 3 times in that computation, and it's 2 times too many. because you can cancel this way. And so you end up with just the 155 times 173 over 270, which is the final result that needs to be computed. Okay, again, these numbers go back to the table. The 155 and the 173, if you look back, the 155 is the total for the row for liberals, and the 173 is the column total for the never smokers. Okay, we're multiplying 155 row total times 173 column total, and the denominator that you divide by is 270, which is the grand total, and you'll see that right here, that 270 in the denominator. So again, what you need to know is to compute an expected frequency for an observation in a given row and column of a two-way table. You use the formula expected frequency is row total times column total over grand total. So let's try these. We're ready to conduct a test for independence using a two-way table. We want to test if political views are independent of marijuana smoking frequency at the 1% level of significance. The hypotheses for this test are: the null hypothesis says the explanatory and response variables are independent, and that never changes. This is just a kind of a sentence we write. The alternative hypothesis says that those two variables are dependent. Okay, so in this context, our null hypothesis would just say that political views and pot smoking frequency are independent. Okay, the alternative hypothesis would say that they are dependent. I'll just say these variables are dependent. Okay. Once you've got your hypotheses straight, there's the data collecting part. So the test for independence between bivariate categorical variables requires that the data be summarized in a two-way table. Row and column totals should be computed so that expected frequencies can be computed as well. The expected frequencies are computed with the formula E is row total times column total over grand total. As with previous goodness of fit tests, we require that each expected frequency is at least 5, and we picked that up in the last lesson. The table below gives observed frequencies O in bold print. Enter the expected frequencies below their corresponding observed frequencies. The first value is already entered. We did the 99.3, and now it says 99.31, so apparently it's a little more precise. Okay, so that was up here, and I'll go ahead and put the 1 after it, 99.31. Okay? Okay, let's do some more. So how about for this one here? The expected frequency is the row total times column total divided by grand total So here, the row total is still 155. For this number, this 35, the column total was 53. And in every case, the grand total is going to be 270. And if you'll do that to a couple of places after the decimal, go ahead and pause if you need to. Okay, so this should come out to be about 30.4. Okay, so we can put that in here, 30.4. the next one down here, expected frequency will be row total, which is still 155, with the new column total down here 44 down there, and always dividing by the same grand total, which is 270. Okay. Okay, so on this one you should get 25.3. Okay. Maybe let's do one more. So down on this row down here, the expected frequency is the row total, which is now 55, times the column total, which is 173, and you divide by that grand total of 270. Okay. So do that real quick. And again, we're rounding to one place after the decimal. Okay. So you should have gotten about 35.2 here. So we'll put that in here, 35.2. Now, I'll just let you take a few moments. Feel free to pause, and when you come back, I'll put the answers in. Okay, I'm going to go ahead and start putting these in. Okay, so you can see the values here. Feel free to pause if you need a little bit of time to get all these written down. Okay, so as before, we are going to have to do the chi-square statistic next, but do remember the requirement for the test is that each E has to be at least 5. So on question 14, it's asking if the criteria are satisfied. The answer is yes, since, now if you look, one of the expected frequencies is 9, which is the smallest one. They have to be at least 5 was our rule. So we can say yes, since each E is greater than or equal to 5. That's our rule. And that was satisfied. Okay. Okay, next we have to do our chi-square statistic. Okay, and what we want to do is copy over our expected frequencies from the prior table. The first 3 numbers here in the expected frequencies make up the first column of the table. So the 94, 43, and 34 are from this column of the table. And so I'm just going to copy over the expected frequencies from there. Okay, I'll just copy that. And I'm pasting in those expected frequencies here. Okay, so that's the first column of the table. Okay, so the next 3 are the second column of the table. Again, I'll just copy those over. And the last 3 are the last column of the table, of course. Now we're working on the chi-square statistic, and again, on the chi-square statistic, we have to sum up the O minus E squared over E computation for every outcome of the experiment. So here we go. First one's done. Okay. Next one, O minus E squared over E. Here, you've got to do the observed, which is 43, minus E, which is the 35.2. Square that, and divide by E, which again is the 35.2. Okay, so run that on your calculator. Okay, and hopefully you'll get what I got, which was 1.7284. Okay, and so we'll put that in. All right, now take a moment and pause the video, and I'd like you to fill out the rest of the table and then do the total when it's done. Okay. When you come back, when you take me off pause, I'll put the rest of this in. Okay, so let me go ahead and start putting these numbers in. Okay, so these are the contributions to the chi-square statistic for every outcome of our categorical variables, and then you have to add these up to get a total. And again, there's been a lot of rounding, so don't be surprised if you've carried more digits than I have, then you're going to get a little bit different answers. Anyway, I got 13.3594 for the total. And don't forget, you should remember, you got to add up that first one. So if you got a different value, check and see if you've added in this 0.1103. Okay. Actually, I'm gonna make a small correction here. Just hang on a sec. Okay, so you might have gotten 13.3600 on this if you use the same value, that 0.1103 in the top row. Okay, so there's just some rounding issues here. No big deal. Those are all basically the same. So our chi-square statistic is this total. Again, this is the sum of O minus E squared divided by E, and that's what we're doing here. So, and that came out to be 13.3600. I'm just going to say 13.36. And then we've already figured out the degrees of freedom. There were 4 degrees of freedom, and that came from the fact that there were actually 3 rows of data, don't count the total row, -1, and 3 columns of data, and again, -1, the last one doesn't count. Okay, so this is just 2 times 2, which is 4. So there's 4 degrees of freedom here. Okay, and we're almost done. We want a p-value. So maybe a little sketch would be worthwhile. Remember, these are always right-tailed tests. And 13 is going to be way up there. So 13.36 is what we're using for our test statistic. Chi-square distribution, like that. The area of the tail here is our p-value. Looks pretty small. Okay. Don't forget degrees of freedom are 4. And also that you're going to be able to go to the p-value calculator on the home page in Canvas for our course to find the p-value calculator for the chi-square distribution. Okay, I'm going to jump over to that right now. This is our Canvas page. Just change the degrees of freedom to 4, like that. And then the test statistic, I think we're making 13.36. Okay, now you can kind of see there's a tail shade. Oops, that's wrong. Hang on. 13.36 is better. And then you can see the tail is shaded down there. And the area of the tail is on the left. Is 0.0096, I guess we can say. It's pretty small. So this is 0.0096 based on the values we got. Different roundings. As you go through this, if you round differently than I did, then you're going to get different outcomes. Small differences in p-values are not a big deal. Okay, and then if you compare the p-value to alpha, again, the p-value was 0.0096. That's less than any alpha we've ever used. So let's see if it's less than what we've got here. We gotta find it. Okay, missed it apparently. So I'm gonna scan through again one more time. Right here, 1% significance level is what they're asking for on page 3. So we'll say alpha is 0.01 as we wrap this up. So it's less than 0.01, which is alpha. Again, oops. Just look at the first 2 digits of your p-value when you compare it to the 2 digits which are alpha. You're looking at 0.00, which is less than 0.01. Okay, even with the 0.0096 there, it's less than 0.01. So we would reject the null hypothesis. We would support the alternative, which just basically says that the variables are dependent. There's no proof of this, but we have strong evidence. Okay, so the data support the claim. That pot smoking frequency is dependent on political views. And that is the last hypothesis test that we will do in a lecture for this semester. That's it. So good job hanging in there, you guys. We'll talk about the review for the final exam next time.